Awesome. Okay, so I think it's time to get started. I hope you all enjoyed your lunch. Just a reminder, my name's Amber Brownholtz. I'm your MC for the Code and Deploy track. Our next talk is actually coming from one of our Trellis, Fred here. And a fun fact about Fred is that he is actually one of the many remote workers at Trello, and he came to us to San Jose today from the great state of Iowa. So I think that's pretty cool. And without further ado, I'm going to hand it over to Fred, and he's going to tell us about changing software like a scientist.
Thanks, Amber. Cool. So hopefully everyone had a good lunch. Everyone have a good lunch. Everyone's all ready to go for an afternoon of talks. Cool. So um, before I talk about changing software like a scientist and the case for safer software and kind of a behind the curtain look at how we make some changes at Trello, I want to share a story. It's April 13th, 1970, and astronauts James Lovell, John Swigert, and Fred Hayes are on their way to the moon. And problem is, Apollo 13 should not have this gaping hole in the side of it. And what has happened, if you know the story, an explosion occurs with oxygen tanks. And now these three men and the folks at Houston have to figure out how we're going to bring them back home. Well, thankfully, they have a lifeboat in the form of the lunar landing craft. But there's a problem with this, is as are building up inside of the module, and they need to figure out a way, using with what they have on them, to filter the CO2 out. So the solution that they end up doing is they literally fit a square peg in a round hole. And they're using the filters that are meant for one module and using it in the other. And with some good old duct tape, they're able to fashion this together and they're able to make it home. And the reason why I tell this story is that change is inevitable and stuff's gonna blow up, stuff's gonna happen, and this happens in software. Thankfully, it doesn't end up usually this bad, but this happens, right? So why does software change? Well, there's a couple of different reasons. And we've seen this ourselves at Trello. So as Michael and Nikita were able to share this morning, we have 25 million users now using Trello. We've had to change to be able to handle this sort of scale. The requirements change. Trello has come a long way from its humble beginnings as just a pure digital whiteboard and sticky note tool. We've talked about power-ups and all these different features and all the integrations that you're now seeing. These are things that are new to Trello and things that we're continuously having to change and modify. We want to make sure that Trello continues to be easy to maintain, so we can make changes in the product and make it easier to use. And sometimes we just want to make improvements, whether we want to make things that allow us to do changes faster or to handle things that we can't predict in the future. These are the sorts of improvements that we want to make, and these are all things that cause software to change. So to go about doing this, typically we might ask how it works now, we apply some changes, and hopefully we don't break anything, right? Good luck. And it turns out this actually doesn't go to plan a lot of the times. And Wikipedia has kind of this list, just very plainly named, of software bugs. So let's take a look at some of those software bugs. So this first software bug is probably the most famous example of this. And can anyone recognize what's wrong with the date there at the bottom? LED signs I don't think existed in the year 1900, right? This is Y2K. So what happened is that developers made assumptions on precision and how dates were stored. And what happened was assumptions were made that 00 to 99 would represent the years 1900 to 1999. But what would happen in the year 2000 then? Everything would roll over again, back to the year 1900. This one is a little bit more serious, but again, software is having, unfortunately, a bad impact here where a bug is causing deaths here with x-rays and dosages that were incorrectly administered. Here is the eastern seaboard in 2003 in the United States with lights on. And because of a divide by zero error, that's what it looks like when the lights all go out. Not very good. And finally, here's a ship, the USS Yorktown, in 1997, dead in the water, a multi-million-dollar warship because of a software bug. So we know we have to make changes in software, and we can see that software is everywhere and has all these unforeseen consequences if we're not careful. But how are we going to make those changes safely? How are we going to ensure that whether we're handling critical business processes or life and death situations, how can we do that safely? And specifically what I'm going to talk about today is how are we going to make refactorings? Refactorings are changes in software where there are no visible changes to the end user. The functionality is the same, but we want to make some of those improvements. We want to make software easier to maintain, or make it scale, or make it faster to run. And there's a lot of techniques that we already use. And there's some great talks talking about some of these techniques even here at Summit. So we write tests to ensure that we have different cases that we're testing against, and we have expectations around those tests. We have tools like Bitbucket to help facilitate code reviews on changes, and we can lock that down in source control so we have artifacts and a change history there. We have specifications that we can make sure are really well defined, so there isn't any room for interpretation. We even have professionals that are dedicated, and it's their job to ensure quality, black box and white box testing, and all sorts of other things with continuous deployment. We might have pipelines or using Bamboo. There's all these things that we're doing, but it seems like we still have these bugs, right? And I think what's happening is that we're just lucky. We're just this icebreaker here in the middle of the Arctic, and we're just happening to forge a path, a safe one, in this wide expanse of user interactions, this ice field. But we could make the wrong turn, and something could go wrong, but most of the time, hopefully, we're just lucky enough to just navigate through this ice field. But in the worst case, as I showed in those examples earlier, what can happen is this, and this is the Titanic. It can all go sinking, and very bad things can happen, just with software. Edgar Dijkstra has this quote about program testing specifically, that it can be used to show the presence of bugs, things that we know about that could go wrong, but never to ever prove their absence. And as an engineer at GitHub has pointed out, let's just assume we've shipped buggy software at some point, thus allowing bad data to be stored in our database and our different data stores. And now that data itself could come up again when it's fetched again, and that's probably going to have bugs too. So how are we going to handle that? And all of the techniques that I've described already, I think, are just techniques of inspection. We're just inspecting and hoping to find the absence of bugs, but we're not really sure how the software that we're changing is actually going to respond once it's in production. So how are we going to solve this? And how, ideally, could we measure twice and cut once when it comes to changing our software? Well, it turns out there's this scientific method, and this can actually be used to maybe solve this. We can ask a question of our software. We can ask what it does, what we're trying to change. We might look into different techniques that we want to apply. Maybe we want to use some new technologies or new libraries. And then we'll come up with a hypothesis. We'll propose a change, we'll do a refactoring, we'll create a new class that we think will do something better. And let's experiment on that new piece of functionality. Let's try it out. Capture some information, capture some data, and then look at those results, communicate them out, and maybe repeat the cycle all over again until we have something that we're satisfied with. So GitHub had this exact same issue. And what they were encountering was, like as we may have encountered in some of our own code bases, there's a corner of the code base which we know works, but it's very old and mission critical, but it might have like some issues. It might be hard to maintain. We're scared to change it because we don't want to break this key piece of functionality. And in this case, this key piece of functionality was permissions. And if you think of what could happen if permissions go wrong, we could leak information to competitors. We could have all sorts of access control issues if we get this code wrong. So what GitHub did was, let's take a step back and we know that the old code works, but let's try out this new code. And what we'll do then is run these two pieces of code in parallel. They capture the results of the new code, and then the old code is what's continued to be used elsewhere across the system. And then they publish both those values, the old and the new, and then they can see if there's any differences between the two. So in summary, that process is first coming up with a hypothesis, experimenting on those, and then measuring it. So let's take a look at an example here in Ruby. So this is just a code block simplified that would have this pullable by method to see if a user has the ability to download source code. And there's their hypothesis. They're going to try this new method has access. There's the experiment. They've labeled it for this particular class and method. And they are measuring the results here. So let's say there is a mismatch between the old and the new pieces of code. Now we have the context, the buggy data perhaps that we allowed to come in to the system that we can then use to recreate the test case. We see there's a mismatch. We can go query the database by the repository ID and the user here and see what values exactly corresponded that led to this mismatch. So they measured those results. One of the things that they wanted to verify was, is this hypothesis actually going to perform the same functions that the old one did? And they can see that most of the time, those changes actually match what the legacy, while it might be not as ideal, reliable code that they know works. But there are some mismatches here in the bottom, some mismatches that they can now go on and investigate. And the other hypothesis they had was, the goal of this refactoring was to improve the performance of that particular method. And they were able to measure that. So the candidate here clearly has better performance, a lower response time than the control does. And we thought this was a good idea at Trello. And we have very similar dashboards that do some of this thing. But as Jeff Atwood said, any application that can be written in JavaScript will eventually be written in JavaScript. So we use a lot of JavaScript at Trello, and that's exactly what we did. We ported over Scientist to be used with Node.js, and if you want to use it for yourself for your Node projects, that's how you can use it. There's a few examples that I'm going to go through in the talk, and if you'd like to download those examples and try them out on your own, that's where you can do it. So the first example I'm going to go through is a fairly simple one. Let's add up the numbers in a list. And this is a fairly straightforward example. As you can see, we're just going to loop over the code. loop over the values in that array, and accumulate that into a variable and eventually return it out. But perhaps you want to refactor it, use a more functional approach that doesn't require state to be stored in that function. So what we've done now is we've created a hypothesis of this functional method, and we've created a science experiment that can allow us to try both the iterative approach and the functional approach. And let's see what that output is when we now enter in values into this sum function. And by default, scientists will just print out to console the results. The value that's actually returned by that function is the old code that we know or think works well. But if there are any mismatches, we can see that printed out here, as well as any context we may have included to recreate that case. So here's an example exercise just for the audience. Can anyone spot the bug that might be in here? So is that in the join case? Yeah, so turns out we were missing an argument that we needed to concatenate those things together. And scientists, while this is a very simple example, could have showed that mismatch. Fred, these are easy examples. What about side effects? What about code that has API calls that are calling out to microservices and other dependencies we have? We have data. None of these examples show how we handle data that we've stored in a database anywhere, or saving those values in a database, or any other sorts of input-output that we need to be doing. Well, there's a process that I've thought of to try to handle this, and it breaks down into 3 steps. First, let's isolate the thing that we're trying to change, instrument that, and then after we've done that instrumentation, apply the side effect. So here's an example of processing a user. In the first example, we can see that there might be a complex date calculator that we want to, that we know works, but maybe we want to try a simpler version. And what we've done there is isolated out the thing that we want to change, and then we're going to instrument it. So we're wrapping a science experiment between these 2 functions. Date processed, when it's called, is still going to use the old date calculation, but we're capturing in parallel what the new date calculation is. Finally, we can apply those side effects and save the user, and we can see the results of that science experiment. What about fetching data? So in this case, perhaps we want to try a new way to save and fetch our users that might be faster. So again, we can set up a science experiment that has the old functionality and compare that with a new data store. Let's say in this case of this semi-autonomous vehicle, there's a critical function called apply brakes. And within that is a threshold as to when the system should apply brakes, maybe at a certain distance when it detects an object in front of it. The existing system might be using proximity radar on its own, but we can try a new system that's also using cameras and with that. The rest of the system is going to use that existing brake threshold value, and that's what's actually going to be used to apply the side effect of activating the brakes. Here's a case study that we ran into at Trello. Trello Enterprise is a product that we have that enables single sign-on. And single sign-on is part of a critical component, which is authentication. Again, kind of like GitHub, making sure that you are who you are, and if you aren't that person, we shouldn't allow you in there. But SAML, which is the protocol used to implement single sign-on, has a lot of variations. There's many different vendors, from Active Directory to our own crowd. There's many different implementations of a quote-unquote standard. But we wanted to make changes. We wanted to maintain it. And despite making those changes, we don't want to break authentication. What would happen if all of a sudden we allowed all these users to log in even though they weren't supposed to? Or maybe we weren't actually enforcing single sign-on. Or maybe maybe an entire company wouldn't be able to log into Trello. So we went through this process of doing scientific side effects. We first isolated that functionality in authentication API. So we broke that out into something that could be separated. Then we capture the old and new results of a new and improved library that we had. And then finally, we authenticated the user and created the session. There's safety in experiments. This frees us to try all sorts of things. If we want to try a crazy new refactoring, we can do it and have a reasonable amount of confidence that that's not going to break the rest of the system, since we're still using what we know works. And what's great about this is we can make statements like, well, we know that the code has run without any mismatches for 30 days, or 2 months, or however long it takes you to get confidence in capturing all those production user interactions. There's a lot of velocity that we can get from these experiments. So since we have that safety, and since hypotheses are cheap, we can try lots of things very quickly and try all sorts of things that we may have not been able to do before because we were afraid of the potentially bad side effects they may have had. This isolation is really hard though, and we have to first construct systems that are able to have this sort of isolation and side effect analysis. And making sure that those pieces are composable is even harder. How to build these loose coupling pieces is not easy. I think it's worth it though. With software so ubiquitous and everywhere, I think there's a strong case to be made to apply scientific changes like this, and we've had great success at it at Trello. And I think you all can also have success in applying the same technique as well. Thanks.